All right, guys. So same issue again. The problem is it works and then stop working, and then my cable doesn't work either. So anyway, so we last time we talked about single cycle design, and we went through this, the details of this design here, various components and the control signals and all those things. If you do your homework and then start working on your projects, you actually get some more details about this. And generally, the idea is that it's good. Okay. The idea is that we want to design your homework and your project such that you also get some idea about things that we discuss. It's kind of a continuation of what we discussed in the class. So the last thing that we discussed last lecture was single cycle has this problem that it's very simple, but it's not very efficient. And by efficient, we mean that if we look at the time it takes for each individual instruction, that time is not the same for every instruction. Actually, if you start working on your homework, you've seen that for store versus load versus R type versus I type, you will see different timing for each instruction. And the main reason is that each of these instructions have different timing, right? So some of them use this. For example, the instructions, some of them read from the memory, some of them doesn't read from memory, and all those things, right? And because of this unequal path, the delays is actually a little bit different from each instruction to another instruction. And as a result, if you want to actually, compute the clock, like what should be the clock cycle for this specific processor, we said that since we are assuming that every instruction has to be finished within one cycle, then our longest delay among all these instructions that we have should determine what should be the clock cycle, okay? And as if you do the homework, you will see, for example, that load word is the slowest, and that's kind of determines what would be the clock frequency. And the results, the problem with this is we are basically slowing down everything because of the slowest. So we're not basically doing it in a dynamic or variable fashion. It's if loads is the slowest, everybody else has to suffer because of that. Okay, and that's not the most efficient, as we said time and time again in this course. Our key thing in designing hardware and designing processor is the efficiency. Okay, so today we want to talk about what should we do next and how we can improve this, right? That's the main question that we want to answer in this lecture and the next few lectures. So we basically we want to talk about these various optimizations that we start from a simple cycle, like single cycle, simple design, all the way to the state-of-the-art out-of-order pipeline processors that we are using these days. So the next few lectures would be around this topic. And if you remember that graph that I plotted in the first lecture, we have various different kind of like eras. And I told you that kind of this era, which kind of in 80s and 90s was the main there was kind of the golden age of computer architecture. That's basically all these things that we're gonna talk about in the next few lectures is around this area. That's like all these macro architectural techniques that we use in order to improve our system. Any questions so far about anything before we get into the new topic? Okay, so in order to understand what we need to do and what we are doing, let's first talk about how do we measure the goodness and quality of our design. Like when we are saying we want to improve this, how do we measure that we indeed improve this, right? In order to understand that, we need to basically define some goals and some metrics for you first, and some ways of measuring the performance. So far we always mentioned that, oh, the goal is designing efficient computers, designing performant computers, but we never actually talked about what is that efficiency? Like, how do we measure that efficiency? So let's first focus on that part, and then we move on to the part that, okay, now we know how to measure it, how we can achieve that efficiency, okay? So the main two metrics that we typically use in order to measure the quality of a design, the quality of performance is latency and throughput. Latency is like very simple, way of measuring things. It basically, we measure time it takes to finish a specific task. Of course, lower is better, which means that if we have lower latency for completing one instruction or completing this program, it means that, our system is more efficient, right? And usually the main unit for it is, unit of time. So seconds, millisecond, microsecond, and so on. A very similar metric to latency is throughput. And throughput is basically a rate measure. Basically, what it says is how much, how many tasks can we do for a given time. So it's kind of like, 1 over the latency in some sense. We're going to talk about that, but it's basically a rate at which we can complete tasks. So if we can finish 5 instructions per 1 second, we say that, for example, our throughput is 5. If we can finish 10 instructions, our throughput is 10, and so on and so forth. And for throughputs, the higher is better, which means that we want to have higher throughputs in our system, right? And we typically measure it in instruction per cycle or bits per second or instruction per second. Just kind of like rate and rational, metrics. In addition to these two, given that we are shifting to other paradigms for computation, including like mobile computing and IoT devices and all those different, new paradigms, there is other metrics, specifically power and energy, that also we need to consider when we are measuring the quality of a design. Power is usually, energy per second, and of course, lower power is better. And the power, then the importance of the power really depends on the application and the paradigm. So if you're talking about a mobile device or cell phone, then of course, generally any battery powered device, then of course, power is more important. If you're talking about like several level, systems that are always, connected to some sort of energy, then power would be less important. Maybe throughput and latency are more important. And of course, the energy is kind of like the product of power and latency, right? So you want to have low power, you want to have low latency, and as a result, you want to have low energy. But sometimes both of them you cannot be achieved at the same time. So one big question is throughput and latency are essentially the same thing? And if so, why we're defining these two different things differently? And for example, if you think about this, let's have these two questions. Like if you have if it takes t seconds for one task, then we say the latency of that task is t. What does that mean? That the throughput is also 1 over t, or is it different? Or look at it differently. If you say it takes t in uppercase second to do n tasks, then the throughput by definition is n over t. But the question is, does the latency is t over n or not? Or in other words, is throughput is equal to 1 over latency, yes or no, or sometimes yes or sometimes no? And any possible answer? Anybody has any idea that whether these are the same thing or not? The answer, someone answered that if everything runs serially, then yes. Any other comments? Yes, that's true. So if, in other words, I'll say it differently. I'll say if there is some form of concurrency, which means that if there are tasks, being executed and being completed in parallel, then throughput and latency are two different things. So for example, like I'm showing it in graphic here, that if you have 3 tasks here, here, and here, and if there are some overlaps between these tasks, then what happens is the time it takes to finish these 3 tasks altogether is t. So this t is basically becomes our latency. And in this case, the individual latency of each of these is T1, T2, and T3, but the throughput of this system is basically like 3 over T. So you cannot say, for example, the latency of this program and this program and this program is T over 3. So this is not the same thing as, let me just, so your latency is not T over 3. Your latency is still T1, T2, and T3, but your throughput is basically the T over 3, right? This would be your, 3 over T. So this would be your throughput. Your throughput is the overall time it takes to finish everything divided by the number of tasks that was finished, which in this case is 3 over T. But your latency for each of these individual tasks is T1, T2, and T3. And if you sum the T1, T2, and T3 is obviously much bigger than T. Okay. So in other words, what we are trying to say here is that if there is some form of concurrency, then latency and throughputs become two different things. And if we manage, for example, to run like 5 or 10 different applications at the same time, then of course our throughput is significantly increased, but the individual latency of this application doesn't change, right? So like parallelism helps us with throughput, but not necessarily with latency. Does that make sense? Anybody? Any doubts? Question? Yeah. So the question is T over 3 is the latency, and I said no. So you cannot say that the latency of each individual task is T over 3. The latency of each task is T1, T2, and T3, but the throughput is 3 over T. Yeah, T over 3 doesn't mean anything. You can say it's average latency. You can say that, but it's not the latency of the application. So the question is, what if they're sequential? And then in that case, yes, you can say that throughput and latency are kind of like the opposite of each other. Yes. So because if you then add T1, T2, and T3, you will get T, right? So your latency in this case becomes the same thing. So the question is, what if T1, T2, and T3 are not equal? Yes, then so it depends. So if you say what is the latency of each individual task, then it's T1, T2, and T3. If assuming that these tasks 3 together creates a group and we want to report the latency of that group, then becomes T1 plus T2 and plus T3. So the question is that if we're assuming the single cycle, then T1, T2, and T3 becomes the same. True. This is just general. It's not assuming that we have a single cycle system or not. And in single cycle, we won't have any concurrency, right? So we have always serialization. So in that case, your throughput and latency are kind of like interchangeable. But what will happen is that once we start describing pipeline, you will see that's exactly where we start getting these gains, because now we start concurring things together, parallelizing things together, overlapping things together, and that way we get better throughput and latency. Okay. So one thing that I want to clarify before we moving on to other things, that in computer architecture generally we use this fairly confusing terminology, and that's the word improve. So whenever I say improve, I mean things get better, but doesn't necessarily means that the value gets higher. Okay. So first of all, if I say that something has been improved by 2.5x, it means that it has been improved by 150%. Okay. So 150% improvement is added to the baseline of 100, so 250% that way. Okay. Or in other words, if your value was 1, now it's 2.5, right? That's how we are using this terminology. The second thing is when we are saying improve, if it's bigger, better, it means that the value has been increased. So for example, if I say I improve the throughput, it means that the value of throughput has been increased. So like for example, it was 5 and now it's 10 or 20 or whatever. But on the other hand, if the smaller is better, then improve means decrease. So for example, if I say by this technique or that technique, I improve my latency, it means that I reduce my latency. Okay. So the word improve means to improve the quality of our system depending on the metric. If the metric lower is better, then improve means decrease. Okay. So don't be confused by this word that I'm saying. And so now let's continue. So let's actually, now that we understand that there is latency and there's throughput, let's now think about performance in general and say how we actually measure performance. And as I said, generally the way that we measure performance is by time, or in other words, by latency. So we usually say that, okay, if we have two computers that do exactly same thing, so the workload for both of them are exactly the same, then we say that this computer is more performant or faster if it takes least amount of time for that computer to finish that task, right? This is pretty trivial. But the biggest question is that, okay, if I give two different applications to a computer, how do we measure time for these, right? So because measuring the time may sound trivial, but in reality may not be something that we can easily measure, okay? In order to measure time, we kind of like follow this this kind of graph, that if you look at the time that we see and as an observer outside the computer, what we measure usually is this wall clock time, okay? This elapsed times or wall clock time, which basically we run the application, we wait for some time, we see the results and say, okay, this is the time it takes for this application to finish, right? But in reality, what happens is that this time has multiple different components. The main thing that this time has is system events and the program events. And you can think about that there are multiple programs that's being executed in this system. The system event is basically what's done by the operating system. So whenever you hit enter and start executing an application, the application first goes through some, complex activities that is handled by the operating system. This includes some access to the I/O and read things from the I/O. Also, some form of computation that needs to be done by the operating system. Then the control will be passed through the program. And again, inside the program, you might read and write from files. You might do some computations and so on and so forth. So this time that we see here is combination of all these things together, okay? And it could be multiple programs at the same time. So what the operating system typically does is context switch between these programs. So it doesn't run A to finish and then run B. What it does is kind of like say, okay, I'm just gonna run a portion of A, then I'm gonna switch and run a portion of B, then I'm gonna switch back to A and run the rest of it, and so on and so forth. And the time it takes to finish this includes both this program and this program altogether. So in other words, to summarize, the time we see and what we can measure easily is this time here. And that time is combination of the system events, the program events, and even the possible context switching that we might have, okay? What we want from a program, typically, when we're saying that whether this program is fast or not, we really need to measure, we really want to measure only this portion of the whole timing here, okay? So this is basically what we call as the word CPU time, or generally the time that it takes for this program to finish, okay? And as I said, unfortunately, we need to also measure all these other junks here, in addition to this only portion that we're really interested in. Because this is really the part that's the program that you write and the time it takes for the processor to actually read those instructions and run those instructions. That's the part that is responsible for that. The rest of it is basically the harness around that code. What we need that harness be in order to be able to interact with the I/O, with the rest of the system, and so on and so forth. Okay, so we usually call this CPU time, and this is usually called the wall clock time or general time. Okay. So now the question is that how we can from this here, how we can get to this point. There are ways that we do that. And I'm going to very briefly talk about that. The good thing about this is that we can measure this very, very accurately, because we can basically use a timer and measure the time it takes to run the application in order to finish the application. But this time is the one that we are interested in. And from now on, when we are talking about improving the time, we really mainly focus on this part rather than this part, okay? So let's see actually how from here we can get to here. And in order to do that, basically what we need to do is first of all understanding how the CPU time can be measured. And the second thing is that if you're saying that, for example, this application has this amount of time, what is the generic and average behavior that we need to measure? Should we just randomly select some applications and run it into our hardware, or should we be more systematic and things about a more efficient way? So let's answer these two questions. So we can measure the CPU time by just running the application multiple times, do the averaging, trying to minimize all these other interference, all these other activities from the OS, or tries to even model the OS and tries to kind of like, measure this. We call this measuring directly. And the problem is it's usually very costly because we need to kind of like, eliminate all these sorts of interferences. The alternative option is that's very popular among performance modeling in different industries and different companies and even in academia, is that we typically rely on what's called a simulation. So simulation is this piece of software that kind of emulates and simulates in some detail the actual hardware. And the nice thing about this is that since we are basically creating our own software, we have full control of measuring each of these components independently. We can, simulate the operating system and the CPU. And given that we actually like having this software, we can then distinguish the time it takes for this one versus the time it takes for this one. Okay. And this is basically like, the key components in any sort of, design and hardware systems, that we instead of like, relying on real hardware and doing the measurements and eliminating all these interferences, which in many cases we cannot really eliminate those, maybe we can actually create our own simulator. Maybe we can create our own kind of like, control environments and then do the measurements that way. And that's kind of the rationale of designing simulators in our system. And that's kind of like your project is kind of trying to mimic that as well. So what we want to do is creating a simple, RISC-V simulator that can basically run through the application. And that way, for example, we can measure the latency and so on. We're not going to go that far and start like, actually using it for useful purposes. But generally, we are going to that direction that we want to creates a piece of software that basically, simulates the behavior of the process. And the use case for that is for measuring the CPU time. So if you would ask, oh, why are we doing this? It's because in reality, there are like, very detailed models that actually design your, analyze and simulate your CPUs for performance reasons. Okay. So that's kind of like, that's how we measure the CPU time. And from rest of this class, whenever we say CPU time, we're talking about that specific program and the time it takes to finish that program on your CPU. We're not talking about the hardness. We're not talking about the IO. We're not talking about the OS and all those things. Okay. So now we know that we can measure CPU time. And let's say you have this piece of software that can accurately simulate the processor. What is the application that we need to feed into this processor, this simulator, to give us the CPU time? Of course, for one specific application, we can say this is the time for that specific application. But if you want to make any comments about, let's say, two different CPU designs and say which one is faster, we cannot just come up with random application and say, okay, I just created this random application and it's faster on this computer versus that computer. That's not the systematic way of measuring these two. The systematic way of measuring these two things is we need to this suite of software called benchmarking, which basically a group of applications, each of which are carefully designed and they have different characteristics. Maybe they use different components inside our hardware, and this way we can basically measure this and then report the average behavior of a processor on this collection of applications. So we usually do that, and we call that benchmarking software. There are lots of benchmarking if you actually search online about CPUs. Typically, they are designed for measuring the performance, but you can, for example, have a benchmark for measuring power. You can have a benchmark that measure how fast your register file is working, and so on. So you can have specific benchmarks, or generally can have benchmarks that's just target the performance of your system. If you search, you will see that spec is basically the one that's very widely used, the SPEC benchmark. And usually it comes with a SPEC 2000, SPEC 2006, and I think there's also a recent version of 2016. So these are a collection of different software, so mostly real software, that some people think about, okay, this is a good representative of all the applications that, normal people, normal users would use. And we're going to run all these things on our processor and measure the average time it takes for each of them, and then report various metrics. For example, how many memory accesses it has, how much time it takes to finish it, and so on and so forth. Okay, so that's the standard way of measuring software using standard benchmarks. Of course, the benchmark also has other applications. So for the architects, for the designer of the software, the main application is to make sure that their design is fast and more efficient and better than the others. But it also used for marketing. For example, Apple, if they comes out and say, oh, this new generation of our processor is faster than the previous generation, this comes up with some graph and some data that they also release. And they show that, oh, they use this specific benchmark or that specific benchmark, and they run it on both of their, their designs and show that, okay, this design that they claim is faster actually achieves better results. Or you can do the same thing, for example, to compare two different companies or two different vendors and so on. So for marketing purposes, also benchmarks are very useful. And then for the users also, instead of you trying to run different applications and see whether this laptop is better than the other laptop, what you can do is that you just rely on these, average behavior of all these different software. Okay, so that's there are lots of benefit of using benchmarks, and that's why they're very, very popular. Okay. So just to step back, we said that we are basically interested in measuring time. We talked about latency and throughput. In order to measure time, we usually rely on latency as the main metric. In order to measure latency, we typically rely on CPU time. And I told you that there is a difference between CPU time and the wall clock time. And in order to measure CPU time, we typically rely on some form of simulation software to test our things. And in order to run different applications and have like a good representative of these applications, we typically rely on benchmarks. Okay, so any questions so far? Okay. So let's now dive a little bit deeper into the CPU time, and just think about what are the important factors in CPU time. Because remember, we want to improve our single cycle design and make it better. Okay, so in order to, and then what we need to do by making it better, we basically want to improve our CPU time. And by improve, as I just said, the improve means reducing your CPU time. So that's the goal, that's what we are looking for. So what are the important factors for CPU time? What are the things that we need to consider when we are talking about CPU times? And this is basically what we usually refer as to the iron law of the processor. There are three things that we need to consider, and we need to play with in order to reduce the CPU time. Anybody has any idea what are those things? Any suggestions? If you want to increase the CPU time, improve the CPU time or decrease CPU time, what should we do? For example, what should we do with the clock cycle or clock time? Increase the clock time to increase the CPU time, or should we reduce it? Yeah, we should increase our clock frequency, because the faster that we can clock, it means that the faster we can finish instructions. So of course our CPU time reduces. What about number of instructions? If you have less number of instructions, then the time it takes to finish them, of course, would be less, right? So if you look at these things, there are actually three things that we need to consider. There's instruction count, which basically says how many instructions are we running for this program. There is cycle per instruction, which basically says for each instruction, how many cycles do we need to use. And then there is cycle time, which basically says how much time it takes for each individual instruction. And if you multiply these three things together, it basically gives you the CPU time, right? So I have each individual instruction takes this amount of time. This is like the number of cycles it takes for each instruction. And these are the number of instructions that I need to run. And if I multiply these three, of course, I'm getting the CPU time. So now let's actually go a little bit deeper into each of them and see what can we do in order to improve our CPU time. Remember, we want to reduce this CPU time, right? So we want to make it smaller and smaller, which means that our programs can be executed faster. Okay, so instruction count, usually we call it IC. And in order to think about what is IC, is basically this, like how large your program is. If your program is 100 instruction, your IC is 100. If your program is million instructions, your IC is million, right? And if obviously for the same hardware, running million instructions takes, more times than running 100 instructions, obviously. So what you want to do is you can reduce your instruction. If you can reduce your instruction count as much as possible, then you will improve your CPU time. Okay, so you might ask, how do we decrease the IC? You can decrease the IC by two things. One is if you use better algorithms. So for example, the question number 4 in your homework 1, right? People come up with different algorithms. Some of them takes like 100 cycles, some of them takes 20 cycles, some of them takes 1,000 cycles. Assuming that all of them run on the same hardware, if they achieve the same thing, of course, the one that has the minimum amount of instruction is the best one, right? So using better algorithms, using better programming languages, using better compilers in order to minimize the number of instructions can improve the CPU time. So there are lots and lots of, work in that domains in order to make things faster. Generally at the software level, like, any efficient, changes that you can make directly, translate into this instruction count. Another important things to think about is, remember we talked about RISC and CISC, right? So if we use something like RISC that basically reduce the number of instructions, that also can potentially contribute to the CPU time. If for the same application we use less number of instructions, of course we're gonna get better performance, better CPU time, right? But we should also be careful that by just using something like CISC, we don't impact the other things like the cycle per instruction or cycle time. And in fact, what happens is that RISC versus CISC doesn't only impact this, unfortunately also impact these things. And that's why eventually people, choose RISC, that although the instruction count is higher, the cycle per instruction and cycle time is lower in those systems. And that's why RISC is usually more favorable than CISC. But long story short, if you can find one way or another in order to reduce your instruction count, then you can improve your CPU time, okay? Moving on to the next one is cycle per instruction, or we usually call it CPI. There's also another metric that is widely used, and that is IPC, or instruction per cycle, which is essentially 1 over CPI. So CPI is cycle per instruction, and IPC is instruction per cycle, which they're interchangeable. And also another thing that people use is MIPS, or million instructions per second. These are like, these are all of them are basically referred to kind of same thing. In various ways. So the numbers are not exactly the same, but the concept is exactly the same. So CPI basically says that the number of cycles it takes to finish one instruction. The simple description for this is that so far we talked about single cycle. So we said that the number of cycles required for every instruction is just one cycle. So for our single cycle design, the CPI is always equal to 1, okay? So there is no way that we can improve the CPI to less than 1 or more than 1. But as we move forward, you will see that the CPI is actually changing when we're changing the design. You got a question? How do I define? So the question is, how do you define cycle? By cycle means the actual, so think about the data path that we had and think about the design that we had. We assume that it takes one cycle, by cycle means clock cycle, and that it takes to finish one instruction, okay? So for our single cycle, we assume that every instruction takes exactly one cycle, one clock cycle to finish. So that's why our CPI is equal to 1. So the question is, how do you account for pipelining? We're going to talk about the pipelining exactly after this. So how do we calculate the CPI for pipelining? Okay. Any other questions? So the question is, CPI is an average metric or the worst case. If there are cases that different instructions use different CPIs, then yes, it becomes a weighted average. So you should say, for example, if I have this group of instructions A that takes 2 cycles, and I have another group of instruction B that takes 1 cycle, you cannot say that my average CPI is 1.5. You should say, how many instructions do I have here? Like if this is 50% and then this is 50%, then of course your CPI is 1.5. If it's not, you have to do the average weight, average sum of these in order to find that. Okay. So what we will see is that the CPI for different instructions when we are moving on to more complex design is not necessarily 1. So what you want to do is kind of like balance between your CPI and all these other metrics like the IC and CT in order to ultimately reduce your CPU time. And this part we're going to actually talk a lot about in the rest of these lectures, in this lecture and the rest of the other lectures in the next 2 weeks or so. Okay. Okay, so moving on to the last one, the cycle time. So the cycle time is essentially 1 over the frequency of your clock, right? So if you improve the frequency of your clock, if you manage to clock your system faster and faster, you are essentially reducing or improving your cycle time. And by reducing your cycle time, you are essentially improving your CPU time, in other words, reducing your CPU time, right? So it's generally favorable to make your system faster, to clock your system faster and faster. And if you remember when we were talking about all these advances in devices and all these advances in technologies, and I draw a plot for you that the clock is kind of like rising in somewhat linear fashion, all these things means that our CT is decreasing and decreasing by generation, and that's directly results in lower CPU time. So that's why we are getting this much performance in our systems. It's not just about instruction count and cycle per instruction, it's also about cycle time and the fact that we have better technologies and better transistors. But as you will see, that cycle time is not just about the device, it's also about your hardware design and your longest path. So remember, for example, we said that in your single cycle, this cycle time is basically determined by your slowest design, slowest instruction. If you manage to somehow improve that design so that it takes less amount of time, for example, for finishing load board, then our cycle times will decrease and our CPU time will decrease, right? So it's a combination of technology and our designs and our decisions that we make in designing our hardware. And that's how we get the cycle time reduced. Okay? So moving on. So that's kind of like it for the CPU time. So CPU time, again, is a combination of 3 factors. Each factor has its own independent kind of things that we can do in order to improve it. But sometimes if you improve one, it might impact the others, such as, for example, if you move from RISC to CISC, you might reduce your instruction count, but unfortunately, your cycle per instruction and cycle time might get hurt. So you need to consider all of these 3 things at the same time. They have equal impact in terms of CPU time. So what you want to do is kind of like coming up with a design to reduce these things, okay? So now that we understand this, we know that what is the measure of goodness. Now let's actually move on from single cycle to more advanced systems. Specifically, what we're going to discuss in this lecture is what's called a pipeline process or a pipelining design, and see how these, by knowing that the goal is basically reducing this CPU time, how we are actually getting this done. What happens to instruction count, the cycle per instruction, and cycle time, and how we eventually manage to reduce the CPU time. Any questions so far? Okay. So remember, the first approach that we said was single cycle design. So we said that, okay, let's assume that every instruction in our system takes exactly 1 cycle to finish. And we said that this is very simple to design because our controller is very straightforward, our data path is very straightforward, and all those things. But unfortunately, the problem with that is that our CPU time is not great. Okay, so now let's change that and move on to the other alternative and think about adding what's called stages. So instead of saying that, okay, every instruction takes exactly 1 cycle to finish, we define our data paths and we divide our data paths into stages and say, okay, each stage takes only 1 cycle to finish, okay? And then the instruction has to go through its stages and then finish the final results. And this way, instead of then thinking about that, okay, this is my data path, right? This is the entire data path starting from the PC all the way to the write back, and say, okay, I need to measure this time, and I need to find the longest path in this, and say this would be the max of this would be my clock cycle. What I would do is that I break this down into stages. And I'll say, okay, I measured this time, I measured this time, I measured this time, I measured this time. And the max of these 4 would be my clock cycle. And of course, since these are much smaller stages, much smaller, amount of logic that needs to be computed, then of course my clock will be reduced, right? So basically, I'm kind of breaking down my critical paths into smaller pieces, and this way I reduce my cycle time. So just to show it in our design, we usually define it this way. So this could be one way of making these stages. Of course, you can make it in many other ways. But let's, for example, assume that we divide this reading, fetching and reading from the memory into one stage. Then we're reading the register file and then maybe doing the immediate generation in another stage. And then maybe doing the ALU operations in another stage, doing the memory read in another stage, and then doing the write back, basically writing into another stage. So basically what we're proposing here is a 5-stage design that instead of for every instruction to finish in 1 cycle, every instruction takes 5 cycles to finish, okay? So 1 cycle for doing this, 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 and finally 1 cycle for writing back the results to our register, okay? So if you're doing that, and now I know that some of you might ask, oh, why we're drawing this line here and not maybe after this, or why we didn't do after this, and all those things. We're gonna get to that part. But for now, let's say that this is something that we're proposing and see how does this help, okay? So if you do that, first of all, you might ask, what is these lines essentially? And what do we mean by stages? Well, these stages are nothing but by adding registers, temporary registers, or what we call pipeline registers into our design. And if you recall about the registers, basically what the register does is remembers what the combinational logic behind it was, okay? So what your register does is basically, if you have this combinational logic, which in this case, for example, this is your combinational logic, because there's no register parts involved in this. So from reading your PC to reading your instruction, everything is combinational. So what will happen is that if you add a register here and here, basically during that clock cycle, this line would be fed from this register. And once the next positive edge of the clock comes in, whatever results that happening, whatever computation that is happening here will be saved into this register. And then in the next clock, this value would be translated into the next stage of our processor. Same story happening here. So for example, what is happening here right now is we are reading some data. So there will be some values here and here. And then what we do is that we add this register, this red line here, that once the positive edge of the clock comes in, whatever value that exists in here and here will be saved into that register. And in the next clock cycle, in this area here, basically. This value would be basically translated into this next stage. Think about these lines as doors that people get into, like get behind one door. The positive edge of the clock comes in, the door gets open, people go into the next room, stays in that next room for the entire clock cycle, then another door opens and they go to the next one and next one and next one, right? So this is basically the analogy that you can think about this, that people start from the first room, there is a door between them, so they cannot just go into the next room. So that was when we had the single cycle design. There was no walls between our rooms, so people get to just freely start from the first room and go all the way to the fifth room. But what we are introducing now is these barriers between these rooms, and these barriers only open by the positive edge of the clock because we are adding registers. And once the door opens, people from one room can go to the next room, and people from that room can go to the next room and next room and next room. And this way, we are basically creating this kind of multi-stage design. And one thing to remember that we are basically showing a simplified design here. So here is not just one register. For every single line that you see here, there is a specific register for it. And these are, again, if you remember, these are not just 1-bit data. For example, this is a 32-bit data. So we need a 32-bit register here to save this number. So whatever line that you see here, and whatever number of bits that you see here, basically that's the register that you need to have there in order to save that results. Does that make sense? Anybody has any questions? Yeah. So the question is that now we are doing this, what happens to our single cycle design? And that's a great question. That's exactly like what we're gonna talk about. Like, first of all, how does this happen? Like, how do we actually implement this? And then I think the more important question is, how does this impact the CPU time, right? So because at the end of the day, remember, we want to reduce our CPU time. Okay. So let me actually go through more of this detail. So basically this lines here, I make it like, more kind of like more elaborate here. And we usually call these registers here, we call it some like pipeline register and call it some name. So since this section here is for instruction fetch, right? So we are fetching the instruction here. This register, we call it instruction fetch / instruction decode. So RIFID, we usually call it. Because this part is the decoding, instruction decoding, and this part is instruction fetching. So this is the intersection between decoding and fetching. This one is the intersection between decoding and execution, right? Because this part is the execution and this part is decoding. This is the intersection between your execution and your memory, and this part is the intersection between your memory and your write back. Okay, so we call this by these names to kind of distinguish and differentiate between them. So that's something to remember. So now let's actually move on to how does this help, and then how we actually implement this first, right? So you might ask, how do we, decide this 5 and not why 3, and why not 7, or why not 100, and where exactly should we, put this pipeline registers? Why, for example, we select this area here rather than, moving it to somewhere else? So the answer to that is that we need what's called a balanced design, because remember, basically your clock cycle, so this is one delay, this is another delay, third, fourth, and fifth, right? There are 5 different delays, and your clock cycle would be the maximum of these 5, okay? Whichever takes the longest, that would be your clock cycle. So it doesn't make sense, for example, to make this much more faster if, for example, this one is much more slower, right? So what you want to do is, as much as possible, have equal length of delay between these 5 stages. If you have this balance, then your clock cycle is basically the most optimum, right? Because you have X1, X2, X3, and all the way to X5. By X, I mean your delays. If you want to maximize this optimization problem, the answer is that these 5 has to be equal to each other. in order to maximize this problem, okay? So the reason that we pick these locations is that if you actually, like, again, use your homework 2 as a practice, you will see that the time it takes, for example, from reading the PC all the way to here is very, very similar to reading the instructions and reading your register file. It's very, very similar to this part. It's kind of like similar to this part, and also similar to writing back the results to your registers. And that's the reason that we make this 5-stage pipeline. You can reduce or increase the number of pipelines. Basically, for example, you can just divide all of them into 5. You also have quantization issue. For example, you cannot divide your memory into smaller pieces because the delay for the memory is something that is always there. You cannot make it smaller. We will have some discussion on that in the next lecture. But yeah, basically, the reason that we come up with 5 is because this is like the best balance in terms of overhead versus kind of like balancing your clock time. Say it again. This one? Yeah. So the question is that we think that this part is happening very, very quickly. So why we are doing this? You can. The problem. So the reason. So this part is much more faster than the rest of them. But think about this, that an alternative to this would have been moving this to here, right? So which means that this part gets longer. And that's exactly the part that we don't want to get longer, because that's the critical path in our system. Because reading from the memory is the slowest, unfortunately, among these 5. So you want to reduce the amount of work in this part. So you move everything from this side and this side, and this is basically just reading the memory. So the question is, what happens to your control signals, and do you need more control signals? And that's a great question. And we're gonna actually talk about this in exactly a few more slides. Like, what should we do for the control signals, and how does things actually moving forward? Before that, I need to explain a few things, and then I'll get to that point. Any other questions? Okay. So an alternative to this, that since we're gonna talk about this multiple times, is that we usually, instead of like showing this to you from now on, we're gonna show you this simplified version. Okay. So I'm not gonna show you the control signals or the whole data path. If I show you something like this, this is exactly our five-stage pipeline. This IM means in instruction memory. This is our register file here. And you see that there are actually 2 lines, which means that there is RS1 and RS2. This is our ALU. This is our data memory. And you see this line is basically the ones that kind of bypass the memory. And this is, again, the same register file here. We just show it this way to say that this is basically the write back part. And this is the reading part, okay? So that's the difference between these 2. But whenever you see this, it basically exactly the idea is showing this. We don't show all the, even here, we kind of make it simplified, right? So we have all those things. We have all those muxes and so on. We just don't show it here to make things simplified, okay? So moving on, let's see, actually, now we are adding this, multi-cycle design. What happens to our CPU time? So of course, as I said, what happens is our cycle time gets reduced. And if we do a perfect job of exactly dividing it to 5, ideally what we would get is CT divided by 5, because we're dividing the entire path into 5 paths, like 5 stages. And if we do a really good job, which in reality we usually don't, in ideal scenario our CT becomes CT divided by 5. So we basically improve our CPU time by a factor of 5, assuming that everything else remains the same. But unfortunately, what happens is that our CPI also increased, because in single cycle, we assume that our CPI was equal to 0, right? Equal to 1. In single cycle, it was equal to 1. But with this multi-cycle design, what happens to our CPI is that now our CPI is equal to 5. right? And if you look at the CPU time, basically, the time is basically, so our number of instructions stays the same, right? So our IC stays the same. Our CPI becomes CPI 5 times the CPI, right? 5 times the previous value. And our CT becomes CT divided by 5. It gets smaller. And if you look at this kind of like, equation, you will see that, these two kind of like cancel each other out. And what remains is the exact same thing that we had before, right? So we basically didn't really improve anything because, yes, we improve our CT, but we, increase our CPI, which these two kind of exactly kind of, cancel each other out. So our CT really doesn't change. But this is kind of encouraging because this is basically say that we no longer pay the penalty of load because now everything can be clocked much more faster. So maybe there are some other ways that if we couple with this, then we can get the performance that we want. Okay, so in the multi-cycle itself, if we just say that every instruction takes five cycles, and we don't do anything else other than that, we can improve our CT, but unfortunately our CPI also will be changed, and these two cancel each other, so there won't be any performance over benefit here. Okay, so let's see what we can do in order to make this better. Let's have a quick break now, and then we're going to come back and talk about that. All right, guys, let's continue. So now we're kind of like, one step in the right direction. Let's see if we can do better, okay? And the idea of pipelining actually comes into play, which gonna help us with the CPI part of the design. So still gonna stick to our stages, but we're gonna use this trick in order to make things better. And that's where the idea of the pipelining comes into play. Pipelining is something that you've seen in your normal life as well. So it's not something unique to computer architecture. They're basically computer architecture people just saw this, that we are using this concept every day. So they apply to their hardware as well. So in order to give you an analogy, think about like, for example, doing your laundry. And let's say you have a bunch of different loads of laundries, like let's say 3 loads of laundry. And let's assume that each load of laundry requires 4 different tasks. You need to wash it, you need to dry it, you need to fold them, and then maybe you need to put it into the closet or just hang them or something like that. Okay, and for now, to make things simple, let's assume that every one step of this takes like 30 minutes to finish. So if you do the simple design, like the most naive kind of like design, what you would do is saying that, okay, I'm gonna put things into the washer and then wait for it to finish, then put it in the dryer, then I'm gonna fold it. I'm gonna put it into my closet, and then once I'm done with this load, I'm then gonna start over, washer, dryer, folding, closet, right? And then I'm gonna keep repeating this until I'm done with my laundry, wait for next time that I need to do my laundry, and that's it. And if I start at 6 p.m., assuming it takes like 30 minutes each, we're gonna finish at 2 a.m. in the morning to do all these things, okay? So that's one way of doing this. Of course, not the most efficient way. The more efficient way is this idea of pipelining, which the idea is that, okay, so since I have my washer finished, and then I want to move on things to my dryer, my washer is now empty and it's not being used and not being utilized. So why don't I like put the next round of clothes into my washer while my dryer is actually do it for the first round? And once this part is finished and I start folding things, then maybe I can and then at the same time the washer also finished, so maybe I can move the washer, the clothes in washer to the dryer, and then now the washer is still open, it's not used. So maybe if I have another round, maybe I can use the washer again and again. So the idea is basically at this point, somewhere in here, especially at this point, you will see that all the 4 resources that I have is being utilized at the same time. And here I'm assuming that all these are automated. So it's not like one person that's doing that. There are like 4 person that can do this at the same time. And so if you're assuming that, basically we can have at best all the 4 items that I have in my disposal, all of them being used and being utilized at the same time. And if I look at this, basically if I start at 6 p.m. for the same exact workload, for same exact timing, I'll finish at somewhere around like 9:30, right? So it's huge, optimization improvement in terms of time it takes. And now you can actually think about this as your instructions and these as your steps, your stages. And what we're proposing here is that don't wait for one instruction to finish and then start the next instruction. Make these stages, your fetch, your decode, your execution, your memory, independent from each other. And once you fetch one instruction and move your instruction to the decode, why don't you actually, fetch a new instruction? If you start things and moving things to your execution, why don't you fetch a new instruction? And in this case, you basically keep the entire pipeline, keep your entire design busy. And this way you can get a significant improvement in your design, okay? So thinking about your pipeline, this is basically what we are proposing here. That again, so first of all, this is like the simplified version of our design. And what I'm showing here is basically these are my clock cycles. So think about this as 1 clock cycle, 2 clock cycles, 3, 4, 5, 6, 7, and so on and so forth. And what we are proposing is that for your first instruction, the first instruction goes into the instruction memory in the first cycle. In the second cycle, of course, it goes to the register file for reading things. In the third cycle, it goes to the ALU. Fourth cycle in data memory, and fifth cycle is in write back stage. But at the same time, in this second cycle, you can fetch a new instruction here, right? And in the third cycle, this one goes into your register file, and this one goes into the fetch, right? So for example, if you look at this point in your program, your first instruction is in write back stage, your second instruction is in data memory stage, and your third instruction is in ALU stage. And assuming that every stage can house one instruction at a time, then at the best we can fill the entire pipeline of 5 stages with 5 different instructions. Okay, and this way we can significantly improve our CPU time, because instead of waiting for one instruction to finish, we are essentially improving our system. And if you want to put this in words, basically assuming that we have an unlimited number of instructions here, so in other words, our pipeline gets filled. If you look at from this side, for example, in the finishing side, you will see that every single clock, there's one instruction in a write back stage. In other words, at every single cycle, we get one instruction to be finished, right? So in other words, essentially our CPI becomes 1 again, because if we keep feeding instructions into our pipeline, of course there will be first 5 cycles to get this filled. But if you have many instructions, that additional 5 clock cycles is negligible. So in best we get really close to 1. So it's slightly less than 1, but very close to 1. Because essentially every single cycle there will be one instruction that is in the write back, and then the next cycle we can say that this instruction is finished. Okay, and the interesting thing about this is that the CT doesn't change, number of instruction also doesn't change. So essentially that problem that we had, that CPI becomes 5 times CPIs, is gone now. So we only have this CT over 5. So essentially what we get from this is that if we do this pipelining in the right way, we don't sacrifice our CT time, then we get 5 times faster processor design than what we got in a single cycle design. Does that make sense? Awesome. So now the question, of course, is how do we do that? Because now somebody asked about the controller, how do we handle these different instructions in our pipeline, because now we are not talking about one instruction and the controller for that one instruction, but we are actually talking about 5 different instructions at the same time in our pipeline. So our controller needs to keep track of 5 things at the same time, needs to issue 5 control signals at the same time, so it becomes much more complicated. So the question is, this impacts your throughput and not latency. Yes, the answer is your individual instruction still takes 5 cycles, but your throughput is now 5. So think about the entire program that is consists of like hundreds and hundreds of instructions. Then the time it takes for all these instructions to finish is now divided by 5, right? So it's this exactly that situation where we have this kind of thing, right? So our T, our capital T, has been reduced. These individual T's are still 5 cycles, but no longer we are adding them together to get our final T, because now we have concurrency. So this T here is now reduced by a factor of 5. Does that make sense? Okay. So now let's actually get into the details of that. Before that, to just give you an overview of like how the timing actually works, I have a table for you to kind of like compare real values for single cycle with pipelining. So I'm showing you here 4 different instructions: load, store, R-type, and branch equal. And I'm kind of like showing the average time of different stages here. In your homework, you will see that it's actually more elaborate. We also give you the details for the multiplexers and the immediate generators and so on. But here I'm just thinking about a simplified version of that. So let's say, for example, your fetch only takes 200 picoseconds, your register file, and so on and so forth. And this is the same time for all of them because we are using the same stage over here. And you see that some of them doesn't use some part of this. For example, store word doesn't need to write to the register, or R-type and R-type does not need to access the memory, and so on and so forth. Okay, so now let's compare our CPU time in single cycle versus in our pipeline design. Okay, so first of all, if you look at the total time for these instructions in single cycle, you will see that the max among these is this load instruction here. That takes 800 picoseconds just by adding these numbers together. Okay, if you just add them all together, you'll see that 800 picoseconds is for the load. For the others, is less than 800 picoseconds because we don't need to do all of those things. In other words, our CT in single cycle would be 800 picosecond, and our CPI would be equal to 1, right? So that's what we know so far. And now if you look at the pipeline design, first of all, your CT would be the max among these stages. So if you look at these max, so you see that your instruction fetch takes 200, register read takes 100, ALU and memory takes 200, and register write takes 100. So if you look at the max, you'll see that these 3 is kind of like, determines what would be your clock cycle. So in this case, the clock cycle would be 200 picoseconds, which is the max of these 3, right? But the beauty of the pipelining is that given that we are sending instruction, in the pipeline, you always have this overlap. Our CPI is almost equal to 1, and we can usually, in this course, we are assuming that your CPI is 1. So we don't go with the approximation. We assume that your CPI gets to 1 if you have enough number of instructions. So if you put these things together, you will see that basically this could be the runtime that you will get for this instruction. Let's say, for example, you have 3 different instructions here with this 200 versus 800 clock cycle. These instructions takes this amount of time for your single cycle, and then added together versus your pipelining basically takes much significant lower amount of time, right? So again, going back to here, your CPU time here would be 200 picosecond times 1 times whatever your IC is. And for your single cycle would be IC times 800 times times 1, right? So this is 800 picosecond and the other one is 100 picosecond. So we are getting like 4 times better in this specific case, better design, because our CT is not 1/5. You see that we cannot get it to perfect 800 divided by 5. We got it to 800 divided by 4. So what we get out of this real example is your CPU time has been reduced by a factor of 4, just by virtue of the fact that we are dividing our pipeline stages into 5, and this timing is basically telling you what you get. Does that make sense? Okay. And what I'm showing here is basically the same thing. I'm just showing it with different graphic. And the big thing here that you can see is basically we are overlapping things together. For now, forget about this part and why the register file is not the same thing. I'll describe it very shortly. But basically what we are saying is that for your pipelining, from 0 to 200, you do the fetch. From 200 to 400, you do the register read, and also you do the fetch. From 400 to 600, you do ALU, reg, and fetch, and so on and so forth, right? So this way, instead of like doing everything serialized, your things in parallel, and that's why you get much more faster execution time for these instructions. Okay, so I hope this would be clear enough to kind of like compare what's the single cycle puts versus pipeline. Is there any question here? Am I recording? Yes. Okay, so let's move on. So again, going back to our design, I told you that we are basically showing our pipeline. Yeah. How much perform? So the question is, how much performance is increased in this specific example, right? So as you can see here, that the numbers that I calculated was our CPU times become 800 picoseconds time IC versus 200 picosecond time IC. Assuming for the same program, we are improving our performance by a factor of 4. So we are saying that we improve it by 4. By 4 times, yeah. Okay. All right, so going back to this, now let's actually talk about a little bit more about the details, like what exactly happens to our data path and what exactly happens to our controller, because that's the main question that we need to really answer. I already described why we are choosing 5 and why we are using this partitioning, because essentially we are trying to balance this as much as possible. So now let's actually talk about the controller, because that's the main part that we need to kind of answer. So the interesting about the controller is that we can use this trick that we also can use registers to save things from our controller. So remember that our controller in our original design was getting instruction in this decode stage, right? So every instruction that comes into the decode stage has to go through the controller, right? So in the controller, within the same cycle here, the controller make a decision about all these control signals, the ALU source, the PC source, branch, ALU up, and all those things that we discussed, right? So all these lines coming from the controller. But the thing is that this also needs to be passed to the next cycle and next cycle. So what we do is that we basically, in addition to having this registers that's kind of like take care of our data path, we are adding this additional registers here that kind of like remembers things from our controller. And what we do is that we keep passing this to the next stage and next stage. And after we passing this to the next stage, we use those that, for example, so we are in the decode stage, so we only need to pass things to the write back stage, memory stage, and execution stage. We already done fetch and decode, right? So there's three more stage that is remaining, right? And then the instruction goes into the execution stage, and there are some control signals that's going for the execution, right? Like the ALU up, the branch, and all those things, right? So we're going to use those, and since we already use those, there's no need to pass them along, right? Because we already used those. So we're going to just send the memory and the write back control signals to the next registers. And in this stage, we're going to use the memory related controller signal here, and we're going to send the write backs here. And then in the write back stage, we're going to use the rest of our controller. So essentially what happens is that for every given clock cycle, the controller needs to decode that specific instruction that is inside this decode stage. We don't need to do anything else. All we need to do is that once we make that decision, we need to pass it to our registers. And those registers, the way that we are basically designing this, kind of like a chain of these registers, they kind of like, pass it to the relevant stages as we move forward. Okay? Yeah. The question is, does this complicate branches in any way? Yes and no. We're going to actually get to that part. So there is this control flow problem that we might have, but generally, for now, we can assume that nothing bad happens to anything else in our systems. We're going to get to that part later on in the course. So the question is, how big are these registers? Depending on what's the size of these lines. So for example, if it's this 1 bit, we need 1 bit register per those lines. If you have 32 bits, you need 32 registers.
The immediate generator that is itself 32 bits.
Mm-hmm.
I thought the registers are on max 32 bits, so do you have multiple registers?
Yeah, the question is that, for example, if you have a 32-bit immediate, a 32 bits register RS1, 32 bits, yeah, you have multiple of this register. So there's not, so as you can see here is also kind of like, kind of showing this with this kind of like, lines here. Okay, red maybe. Yeah, you see these lines here. It's basically kind of indicating that these are different registers. To make things simple, we just show one rectangle. In reality, these are different registers. Okay. So the question is that since you are using these registers to kind of save values, are you using your temporary registers or using your save registers? So these registers, first of all, are different from your register file. So these are additional registers that you're adding. These are not something that you can access in your ISA. It's not transparent to your software. These are just part of your data path that only hardware has access to. So you cannot write to it, you cannot read from it, you cannot change it in any way, and there's nothing to do with your register file or your X0 to X33, 32. These are completely different registers. We call it pipeline registers, and we usually refer it with these names like XMEM or IDFD and so on.
So is there an optimization or is it like the skips, like the 2-stage?
So that's great question. So the question is, there are some instructions that, for example, needs to bypass the memory, right? What should we do with them? Should we like, bypass the registers as well and then kind of like, skip them? Usually what we do is that we don't do that because that complicates our design, because we need another control signal to tell the registers to skip or not skip and all those things. Once we move forward, you will see that there are these things called hazards, and there are these things called branch prediction, branch misprediction. And that's where you're going to see that we actually need to manipulate what needs to be stored and what needs to be passed on and so on in these registers. So yeah, short answer to your question is, for some reasons we do that, we skip this saving, but not for skipping specific instruction, because this is a trade-off we made, that it's easier for us to keep all the move things, everything forward, rather than just keep checking whether this is like, R-type instruction should be like, skip this register or that register. Also keep in mind that if you skip this, for example, if you want to skip this memory part, right? So you want to directly from your ALU go to your write back stage, assuming that this is an R-type instruction, has nothing to do with the memory. Think about that. Your pipeline is already occupied with previous instructions, right? So there is no space here. So going back to your, for example, your laundry analogy, let's say we have the washer, we have the dryer folding and putting things on your closet. Let's say for some reason we want to skip the drying and then we move on to the folding. But think about that, folding is one person that doing the folding for you. And if you say, oh, I don't want to do that, there's already something coming out of your dryer and needs to be folded. So you cannot put two things for the folder to fold, right? So it's kind of like your pipeline stage is already occupied with the previous instruction, so you cannot really move it to the next instruction. So that complicates things a lot. So again, we won't skip things because of those reasons. Any other questions? So the question is the data, the kind of like, everything, your controller and your data in your data path kind of move on to the next cycle and next cycle, every clock cycle, regardless of whether we're going to use that stage or not use that stage, just things move on. Yes. Okay. So now we know that kind of like you take care of the controller. This would be basically the design, the updated design that we were going to have with the controller. So as you can see here, basically what we have added here is these blue signals here. And what you can see is that basically the control signal still gets the instruction from the decode stage, but then pass these control signals not directly to these lines here, but to the registers that are relevant to that stage. Okay. So we don't do this anymore. We just pass this into our pipeline registers. And now, for example, let's see that we want to use our ALU source. The ALU source gets its signal from this register rather than getting it directly from the controller. Still, the source eventually goes into the controller, but the timing is the important factor here, because remember, you have one instruction here, a different instruction here, a different instruction here, different and different. So you cannot use the signal that you're generating for your controller directly into your ALU, because this is from the instruction that is right now in this stage, and this instruction and these instructions are different, and as a result, the control signals are also different. So what you need to do is making sure that during your decode, you pass the correct instruction to your controller, you generate those, you send it to your registers, and then the next cycle here would be the control signals that generated in the previous cycle here, okay? So it's kind of the notion of timing that you need to now add to your understanding of the data path. Previously, in the previous lecture, we talked about this transparent data path that everything was exactly one instruction. So things are kind of flowing from left to right. But now what I'm saying is that things are now blocked by this register. So at every stage, we have a separate instruction. So lines and values here are different than lines and values here, because these are two separate instructions. Does that make sense? Anybody has any doubt about this? Awesome. So moving forward, let's actually think about a few things. So first of all, what you will see here is that, for example, this thing here is your, this thing here is your RD. And instead of moving your RD directly from your instruction to your write register, you will see that this RD is basically first passed to your registers and kind of like coming back here from this port here. So basically, this point here is not same as this point here, although they're coming from the same source. These are two different snapshots of the time. This is from the instruction in this stage. This is from the instruction from previous stages, from previous. So for example, if you have an add, a subtract, an XOR, let's say, for example, your add goes to the decoder, then your add goes to the execution, then your add goes to the memory, and now your add goes into the to your write back stage. So this signal is from your add, but this signal here is from whatever this instruction is. So let's say, for example, this is memory. So this value here is not same as this value here. Okay, so this is very important things to remember, and people keep making this mistake and thinking that, oh, why don't I just directly connect the RD to my register file, same as what we did for the single cycle. That's the reason, because timing wise, value wise, these are separate things, because we want to push everything into our pipeline in order to get the CPI equal to 1 that we want. Yeah. So the question is that, does that mean that we need 2 address for a register? What do you mean by 2 address? So we still do have, right? I mean, in our original one, we also had that. So we still have RS1 and RS2, which coming from the same cycle as decoding, which was fine. And then we have the address, this one, which is our RD, that is coming from our write back stage and not from our decode stage. So we still have 3 addresses, if you remember, similar design. So we didn't change any component here. So exactly the design that I described you last lecture. What we are changing is the way that we are connecting these lines and these wires together. And some of them are coming from these registers, some of them coming directly from the wires. And the reasoning for that is the timing difference and the difference of instructions. Okay? Any other questions? Okay, so that's one thing to remember. And there are lots of other examples. If you follow all these lines in the data path, you see, for example, your branch is actually coming from here instead of coming directly from here and all those things. So I recommend to actually take a good look at this design and making sure that you understand all these lines and how they're actually, being modeled. For example, your 0 is not going straight to this, doesn't go straight to this gate here. It actually goes through the register, and in the next cycle actually goes into the gate, right? Because this gate is in the in the memory stage and not in your ALU stage. Why we're doing that? Again, because we don't want to create a critical path. We want to make sure that all these stages has the same amount of timing. Okay, so keep a very good attention to all these lines here and where we read these things, because that changes the functionality of your code and change the functionality of your processors. Okay, there's a reason for all of these things, and the reason for that is we want to make a balanced design. So the question is that you said the design is the same thing as simple, but we are just pointing to different values at different times. Yes, exactly. So we are doing the exact same logic that we described to you for how to create our ALU control, how do we create our control signals and all those things. We just, the timing of them are different using these registers, this pipeline registers. So we kind of like say, oh, instead of 1 variable, we have 5, and then you just need to read it from the correct one. So the question is that, do you get into the problem of trying to read and write from the same register at the same time? That's a great question, and that's exactly what we're going to describe in the next lecture. Well, next slide, actually, what we need to do. But yes, we will run into that problem. Yeah, that's a great question too. Does PC have the same clock cycle with other registers? And yes, all of these registers all have the same clock frequency, same clock. Okay, so let's quickly finish this discussion. So yeah, that's kind of like, it for the design. I'm not going to go through the rest, but as I said, like, there are things that, like, these are not the same thing. Just please pay attention to the wiring and the reasoning for the wiring. If you have any question, let me know, and you can ask in your design. I also described the controller and said that basically the controller is not directly connected to all these things. It actually, the controller also has to go through the registers, similar way that we are sending this data to our registers, right? So that's something to remember. We also, the way that we are showing this is also graphical, as I already discussed to you, right? So for example, let's say we have 4 different instructions: the add, load, and add. The way that we are showing this is that this becomes basically your add. These are the cycles, by the way. So this is one cycle, first cycle, second, third, and so on. So in the next cycle, your add goes here, your load goes here. In the third cycle, your add goes here, your load goes here, your the other load goes here, and so on and so forth. So if you look at the snapshot of the time, so this is basically one clock cycle if you look at it this way. If you look at it this way, you'll see, for example, your add instruction now is in the ALU. Your first load word is in the register file. And the second load word is in the instruction fetch part, right? So the question is, what happens if this second instruction needs to read something that the first instruction needs to write back? That's a great question, and that's what we call data hazard. And that's actually a problem that we need to solve. And we're going to talk about it in the next lecture. For now, let's assume that things are safe, which means that they are independent, completely independent from each other. So I can just, feed them into our register file without being worried. So if this one needs to read x1 and x2, and this one needs to, for example, read x12, this one doesn't write things to x12, for example. Although that in this specific example, I do that, and that's a data hazard. And that's great that you can catch it. But for now, let's assume that these are completely independent. Okay, so this is another way that we show this, and we're going to show it a lot, especially when I'm discussing data hazard. So just keep in mind that this is another way of showing the same thing. So somebody asked about what if we want to read and write in the same cycle, and that's the last thing I want to discuss today, and that's the concept of half cycle. Okay, so if you look at this shaded area here, you'll see that not all of them are white, some of them are white, and some of them are gray. The gray is actually the part that means that that's the time that this specific unit is active. Okay, so if you pay attention, you will see that whenever you want to read, if this is one clock cycle, so basically this is one clock cycle, we read in second part of this clock cycle, basically like at this point. And we usually call that a half cycle. So basically, if this is the full cycle, right? So if this is your full cycle, we are reading it in this second half of our clock. And the reason for that is that this allows us that if you always say that if write happens in the first half cycle and read happens in the second half cycle, then we can safely write and read in the same cycle. The writing part will happen in the first half cycle. The reading part will be happening in the second half cycle. The reason that we are writing in the first half cycle is, remember, your write is synchronized with the positive edge of the clock. So once the positive edge of the clock comes in, then you have to write. And what we're arguing is that your write should at most takes this amount of time. So whatever your clock cycle is, your clock divided by 2 should be the maximum delays that it takes to write something. And that's very easy to achieve. So if we do that, then when we are reading, we have to wait for one half cycle and then read from that register. That is guaranteed that if something needs to be written to that register file or into that memory, so pay attention that the memory is basically the same thing. If we need something to be written to that memory, we write it in the first half and read it from the second half. Okay. So with this, we basically if, for example, look at this example here, if we need to write to X12 here and we need to read from X12 here, with this half cycle technology, this half cycle, contract, we are safe to do that. The only downside is that we are saying that our writes should happen very, very fast, and our read should also happen very fast, because we were assuming that our reads needs to be less than one cycle and our writes needs to be less than one cycle. What I'm saying now is that your writes and reads should be less than half cycle. Okay, but the good thing is that's not any big issue because it's very easy to achieve that. Any question here? Okay, so in order to remember which one was half cycle, remember that always when we see the gray, it means that it's active. So for example, in this case, this is the write back stage, and we are writing to our register file. That's why this part is gray and this part is white. Versus in this part here, we are reading from our register file. So this part is white and this part is gray because we are reading it from it. So we're doing it the second half cycle. Okay, does that make sense? And another thing that you see in this picture is that, for example, for add, which is an R type, our memory is also white, which means that we are not using our memory. Versus for our load, the second half of our data memory is gray, which means that we are reading from memory. If we had like a store, you would have seen that you have a memory that this first part is kind of grayed out. Okay? All right. So that's it for this. And then after this, I'm going to talk about problems that we're going to face with pipelining. One last thing I want to discuss is your project. If you go to the website, you will see that the project is out. I put the description. I asked the TAs to also describe what you need to do in your project. Please read the project description before going to your discussion section, either tomorrow on Friday, and make sure to start working on it early. Okay? Thank you.